Hi everyone, welcome to Ground Zero AI. So we are into lecture 4 of Foundations of Linear Algebra course, and today we're gonna see Euclidean form, pivot and free variables, and rank. So before moving forward, we're gonna see what's the motivation behind studying these topics. So why do we care about Euclidean forms, pivots, and rank in linear algebra? So the concept is like solving linear equations systematically, understanding linear dependence, independence, and solution spaces. So here some key questions arises. So how can we simplify complex system of linear equations? Or what exactly do pivots and free variables mean intuitively? Or how does rank tell us about the dimensions and solutions of a system? So so before we're gonna start, let's start with a system of linear equation, and we'll kind of revise the basics. So okay. So first thing, we have a very fundamental equation known as like which represents systems in very matrix form. That's called Ax equal b, right? We have Ax equal b. Just one second. So we all know this equation, right? Ax equal b, and so this is kind of an example to visually illustrate a simple system. So I'm gonna give a geometric interpretation here. So intuition is like we kind of show that these planes and lines intersect in a space, right? Like if you can see here, these are some planes P1 and P2, and here are some lines X1, X2. So geometrically, these planes and lines intersect each other. So this is kind of a simple system that is interpreted by linear algebra and with correlation to geometrics, right? So let's get back to what is a Euclidean form and what's the basics of it, right? So, so it starts from REF. If you go to this, okay, REF. So REF stands for row Euclidean form. That is kind of it like visually it can be shown as a staircase structure. I'll be showing in the next slide. Or there's one thing also called reduced row Euclidean form. Basically the leading entities there are exactly one. So let's start from why we need Euclidean form, right? So the first thing is like it is very simpler to see solutions with those, and it provides clarity on linear dependencies. Uh, Also, in background, I have mentioned that we have studied Gaussian elimination in the last lecture, right? So what was Gaussian elimination about? So it's an algorithm to solve a system of linear equations, where we have seen that we do some operations to reduce matrix to in a form that is called Gaussian elimination. And after this Gaussian elimination, the Euclidean form of matrix is achieved. And as I said, it's a better way to visualize a matrix. And what is Echelon form is all about? It's basically so this method can be used to compute the rank of the matrix. As I've said, like when you are given a matrix, so you reduce it to a clear form and do some operations to get the Echelon form, and after that we get what is called rank of the matrix, right? Next thing is like all entries in a column or leading entry as well. We'll be saying to this what is that about. And the third thing is all non-zero rows are above any rows of all zeros. The leading entry of any row occurs to the right of leading entry of the row above it. So this may seem complex as we are just reading it out, but when we visualize a matrix and we'll consider all these 4 points, we're gonna see like how it's gonna look like. Cool. So let's start from here. So let's visualize from this matrix, right? So we're gonna match all these 3 points uh, about the conditions of Euclidean form, and we'll verify if this matrix is Euclidean form or not. So the first condition says the entries in the column below a leading entry are zero. So what is leading entry? We first need to define it, right? So leading entry is basically for any row or column what we are considering. The first element should not be zero. So here in this first column, you see this 5 is the leading entry. One won't be a leading entry because in this row, like 5 has already been occurred. But when you see the second column, right? So here you see 0 is there. So this thing won't be a leading entry. But yeah, 1 is there in this second row. So this would be a leading entry. Similarly, in this third row, you see there is no leading entries, right? But yeah, minus 5 is there. So yeah, all entries in a column below leading entry are 0. So yeah, this is leading entry for the first row. 1 is for second row. And all non-zero rows are above any rows of all zeros. So this means that if there was any row which is just 0 entries, right? So so it won't be above uh, of any non-zero row, right? So if you see, so here this is a non-zero row. Let's say this second row, like as you see, this is non-zero row. So this will always be above of any. row with having all zeros. So if this row has all zeros, 0, 0, 0, 0, right? So this non-zero row will always be above of it, right? So this is one of the conditions of Echelon form. The third condition says that the leading entry of any row occurs to the right of leading entry of the row above it. So this is what I mentioned what leading entry is about. So this says that the so just focus on this one, right? I'll explain this third this condition with this one uh, value. So the leading entry of any row, so one is the leading entry here, I'm just going to verify it, occurs to the right of leading entry of the row above it. So you see on the row above, 5 is the leading entry, right? And it says that the leading of the second row will occur to the right of this leading entry. So yeah, it clearly says that one will be the leading entry here. But yeah, this won't hold for this thing, because you see there is no leading entry here for this uh, third row and third column value, right? So yeah, this all three conditions about Echelon form. Now let's see what are some of the examples which are not in Echelon form, right? So if you see this matrix, so here you see we have the second row as a zero value row, right? So this kind of cancels this second conditions. All non-zero rows are above any rows of all zeros. So here this is non-zero row, but this is below of this zero. So this is gonna cancel this condition. And similarly, like if you see this matrix, so here the condition which satisfies is the first one only. All entries in column below leading entry are zero. So one is the our leading entry for the second row, but the value just below it is one, which is non-zero, right? So this is also not an Echelon form. So before we move next, let's just revise what we have just learned in Echelon form and what is it about. So Echelon form is just a like we usually say is a row Echelon form. It's an arrangement of matrix rows here, looking like a staircase, if you see, right, going down to the right. So each step in this case is called pivot, and which is also known as the leading entry of a new row, right? So rows entirely of zeros, if there are any, go at the bottom. This is also one of the conditions of Echelon form. Leading non-zero entries shift to the right as you move down to the rows, right, as we go down. And there may be a question that why staircase or why there's an Echelon form. So it isolates dependencies, so each row, clearly reveals if it's adding genuinely new information or just reiterating something known from above rows. So we are just removing what is called linear dependencies. So this is much like how you peel layers of redundancy until only independent information is available. And this is one of the key concepts when you go to rank, right? So, and how do we get there? So you are allowed to uh, do three logical operations without changing the essence of the equations. So the first is you just swap rows. Or you can multiply a row by some non-zero constant, or you can just add multiples of one row to other, right? You can just add multiples of one row to other. So these are some of the kind of operations you can do to get to the Echelon form, right? And so like if you go to the geometric interpretation, as I said, if you have equations representing planes in some 3D space, you can see here. So here what happens is so these row operations are like changing your viewing angle or scaling your measurements, like this x2 can be 2x2 or 3x2 as it goes. It doesn't change the planes themselves, just how you represent and see them. So this is all about Echelon form. Next, we're gonna see pivot and free variable. So first understand what exactly is a pivot, and we'll see next. Okay. So a pivot is the first non-zero number from the left in each row once you have Echelon form. So the first condition is you should have Echelon form, and it is the first non-zero number from the left in each row. So it marks the columns with essential or kind of efficient information. So this, like, we are referring these variables as columns only, with having leading non-zeros for each row. Otherwise, the variable will be called free variable. So it's kind of a counterpart of pivot. So the next thing is like, what is the intuition behind pivot? So imagine we are building a structure like a bridge or a house, and each pivot is kind of analogous to a critical pillar or support. Just remove it, and the structure changes fundamentally. So mathematically, pivot position identify which variable or column bring genuine new information. As I said, it's a leading non-zero, right? So that cannot be expressed by combinations of previous columns. Again, just like removing linear dependencies. So columns without pivots are like redundant beams, or we call free variable, that may support structure but don't uniquely identify it. So, so pivot columns are also related to independence. As I said, pivot columns form a basis. This means that they are minimally sufficient to span or represent all essential information in the original system. So maybe like just two of the rows can span all those matrices involved, right? Count of a pivot elements tell us how many fundamentally unique direction or dimension exists. So this thing comes into the picture when you are looking up to number of solutions, unique solution, and something. These play a very pivotal role, as I said. Next thing is understanding free variable that express infinite possibilities. So what are these free variables? So variables corresponding to non-pivot columns, as a general intuition says, but these variables can be freely chosen, like taken any value, and solutions still hold. So they represent the flexibility of kind of redundancy in the system. And why do free variables exist intuitively? Because so let's imagine we have two identical equations, equation one and equation two, or two parallel lines. So two parallel lines should be okay, like it can be 2x plus 4y equal 8, and just a multiple of that equation. So let's say we have a kind of a parallel line or two equation. The second adds no new information. It's just a continuation of the first, right? So this redundancy manifests as freedom in variables. You can pick any value for certain variables and still satisfy all equations. So geometrically, these free variables are they imply just infinite solution performing pipeline, forming a line, plane, or a hyperplane rather than a single intersection point. If you see this equation, so this is I see this is not a equation which has many infinite solutions. It's just like it will be one unique solution, right? So here these pivotal and free variables come into the picture. So let's see this example. We have this equation as 2x plus 3y equal 5 and 3x minus 2y equal 9. So we first take this equation to matrix consideration. So we have 2, 3, 3 minus 2, where 2 is called pivot, and this 3. So basically, see in this Echelon form. So we have this first non-zero entry, right, in the first row. So this is our pivot for this first column. So this is pivot column, or just a like if you represent it by x, we'll call it a pivot variable, right? Cool. I guess this is clear to this part. Let's go next. Yeah. So next comes coefficient and augmented matrix. So this is just a form of matrix where you kind of divide, not just divide. You have the system of linear equations. You just put in a different fashion for both. So in coefficient matrix, you just put what is in the left side of the equation, or the values basically, and in the augmented matrix, you put the values in the left side of the equation as A, but the values on the right as B. So this B matrix, this B thing is, this column doesn't belong to any particular variable. So we don't associate free column or pivot column to this column, right? So this is what we call as augmented matrix, and this is our coefficient matrix. It is clear up to this part. Next comes rank. So yeah, so far what we have seen is just a kind of uh, basics or foundations what led us to rank. So let's just go what rank is. So the rank of a matrix is the number of pivots it has after Echelon form. So with intuition you can say that rank counts how many equations or rows or variables we call columns genuinely matter, or by genuinely matter I mean how many of them are independent, right? So if you see a summary of rank, what it is. So if you just wanna look what how to calculate rank or something, so you just say number of linearly independent rows in the matrix, or linearly independent columns, or number of pivot elements, or number of non-zero rows in a clean form of matrix. So we have an example here where we need to find rank. So what we'll be doing, just my approach will be finding the pivot element of this matrix for each row, and we'll calculate the rank. So for this, we have this non-zero leading entry for this first row. So this is one pivot element. And for the second row, this one is also a pivot. For this third row, this is also a pivot, and 3 is also a pivot. So we have for this matrix, we have rank as 4, right? So this is a way to calculate rank, as I said, and it how we go to calculate rank. There's a simple procedure. So we have a matrix, right? So so do your row operations, or what we say row reduce row Echelon form operations, and convert it to Echelon form, right? Once you have Echelon form, you can easily find rank with just above methodology, like finding number of linear independent rows, columns, pivot element, or non-zero rows in the this Echelon form of matrix, right? There is a note as well. So first thing is a rank is always positive, and the rank is zero for only for zero matrix. And number of pivot plus number of free variable is the total number of columns. As you can just see, so we have total number of columns as 4, and we have there is no free variable. Only we have 4 pivot variables. So 4 plus 0 equal 4. That justifies that number of columns. Total number of columns is the sum of free variable plus pivot variables, right? And to better understand or visualize it, we can quantify rank as an essential complexity or dimensionality of information within the system. So if something is high rank, right? So that means that it has many unique pieces of information, or let's say fewer solutions, possibly just one, right? But if something has a lower rank, so it means that like lower rank relative to number of variables. So it is a redundancy, right? So so it has more free variables. That justifies it has infinite solutions. So let's also kind of visualize its connection with the dimensions. Rank equals to the dimension of the column space, right? That how many independent directions your columns present, and rank also equals the dimension of the row space. So how many independent equations you genuinely have. So I guess I can give you an example here. Let's take this matrix into consideration. You have 1, 2, 3, 2, 4, or just a 6. Okay. You have again 1, 2, 3, right? So in this matrix, you see, so clearly the second and third rows add no new information, just like you see, this is multiple of each other. They, of first basically. So Echelon form reveals that there is just one pivot. Uh, so you have just one linearly independent row. So you can just say that rank is nothing but 1 year. I guess this is all about rank. Okay, kind of summarize this whole video what is all about. It was just the basics of rank, pivot, and free variables and Echelon form. So Echelon form was basically an arrangement of matrix into clear structured staircase steps. Pivots are basically that indicate independent or essential columns or directions or dimensions. Free variables reflect a redundancy, providing infinite flexibility in solutions. And rank is just that count number of pivots quantifying real information complexity, right? So yeah, let's catch up again in the next video. This is all for this. Thank you.